So, ladies and gentlemen, welcome to Southwestern Oregon Community College for the second of 3 geology lectures in the series this year. In a moment, I'll introduce Kathy Cashman, but if you haven't looked already, if you could circle April 24th on your calendar, we've got the scientist in charge of Yellowstone is going to be in town to talk about the fact that there is a giant volcanic caldera in Yellowstone National Park. And so this is the Year of the Geology lecture series of death and destruction. Sometimes it just happens that way. You'll be happy to know I haven't started working on it, but we may be trying to go for a LiDAR talk by Ian Maiden next year. I have a supposed connection with Chris Goldfinger on some of the breaking news in Cascadia, verbal commitment from Carolyn Dreiger for what will be almost maybe the 3 in a row volcano talks, but sometimes that's just how it goes. The state geologist and a couple more ideas that are percolating back in the back of my mind. To get these folks here, we need a little bit of support. One is obviously the community college, which on a very real way provides this hall as well as the tech support, and out there in video land now, also a live web stream. My preference is that you stay here because you can always hear it. And I saw Kathy actually give a talk at GSA where there was no microphone or anything, everything went. And she still went through. I won't do that anymore, even though I could, just because of the web stream feed. If you walked by these handy-dandy little sheets that ask for your name and birthday, please sign them on the way out. If you didn't on the way in, take a minute, because there are a number of organizations that we've dealt with over the years that request to basically proof that you bring in over 200 people if they're going to support bringing people out or sending them to you for free. So by doing that, you help us bring other people in. Some of the other folks that are supporting this lecture series this year include Oregon Resource Corporation and also a grant that I got from the National Association of Geoscience Teachers in honor of Dorothy Stout, who passed away several years ago. This evening, Kathy Cashman comes to us from the University of Oregon, where she's a volcanologist and currently serving duties as department head of geology, which is a thankless job anytime you end up in those types of administrative positions, but she's doing a wonderful job there. It's graduate student weekend where they're looking at the next batch of graduate students, and so she still ended up coming over here, which I'm eternally grateful for. Kathy got her BA at Middlebury in Vermont, and I asked her this afternoon how she ended up in New Zealand for her master's degree. And those of you that are students and potentially planning on future education, her response, I think, is something to consider. She said, well, I had a friend that was a year ahead of me, and they had gotten a scholarship to study someplace, and so they said, well, if you don't apply, you won't get one. And so she ended up for her master's degree over in New Zealand and then finished up with a PhD in Johns Hopkins. She's been at Princeton, she's worked for the USGS, and something that I think is also important, not only is she a world-renowned researcher, but also an excellent educator. And one of the simple ways of defining that is the fact that she's a Phil Knight professor at U of O. And now that hopefully the remaining folks have wandered in, again, actually, one other thing. If you have one of those electronic devices, please pull it out of your pocket right now and turn it off. No, don't smash it. That's usually my line. But please take it out, turn it off. And without further ado, Dr. Kathy Cashman.
Well, thank you very much. It's really fun to be here, and you have a beautiful facility. I'd been out to OIMB, but I hadn't been on this campus, and I'm impressed. It's a nice campus. It's fun to be here, and in particular to talk about Mount St. Helens now, because we're coming up on the 30th anniversary, which is a little sobering for me to realize I've been working on the volcano for 30 years. But we won't go there. So this evening, I just want to tell you some stories about what's happened to the volcano in the last 30 years. And those of you who've studied geology know that usually when geology is described, you talk about processes that take place over millions of years, and all the excitement happened hundreds of millions of years ago. Well, I study processes that in a very short course of minutes, hours, transformed a mountain, and then have continued to transform the mountain through a second eruption. And this is a photo that was taken last summer. So we've seen a mountain destroyed or partially destroyed, and now in the process of rebuilding. And this evening, I wanted to try to weave together a few different narrative themes. One is a personal narrative, and I'll start by telling you a tiny bit about myself and how I ended up becoming a volcanologist. And then a historical narrative, because geology is a historical science, and volcanoes all have their histories. So I'll tell you a little bit about Mount St. Helens history. And then also give you some glimpses into how this particular eruption has really changed the way our discipline of volcanology works. We learned a huge amount from Mount St. Helens, and we continue to learn a huge amount from the volcano. So just an overview, I'll give an introduction to me, an introduction to the volcano, and then we'll look at the activity that occurred from 1980 to 1986, so that's the first eruption of the title. And I'll tell you something about what happened, and then a little bit about how we interpret what happened. And then we'll look at this time interval from 1986 to 2004, where it appeared that not much was happening unless you can look underground, and we'll see that. And then we'll look at the second eruption, the 2004-2008 activity. So first of all, me. That was me in 1980. And at the time of the eruption, I was working for the US Geological Survey in Woods Hole, Massachusetts. And I had been in New Zealand, as Ron said. I'd worked on some volcanoes there. So when all of a sudden a volcano started erupting out here, I started whining. This is another lesson to all the students. Occasionally whining works. I was complaining to my boss saying, you know, here I am on the East Coast. I was actually on a ship off the East Coast, and I said all the actions in the West Coast, and he said, don't whine to me, whine to someone who can do something about it. So he arranged for me to talk to one of the USGS people in Reston, Virginia. And then they called me, or my boss called me into his office for a conference call, and they said, well, what we really need out at Mount St. Helens is someone to talk to the media. We need a public information scientist. And my first response was, no way. But my boss said, look, you've been wanting to get out there. It's a foot in the door. Go out and do it. I thought I was going to be there for 2 months, but I was there for almost 2 years. I had my 15 minutes of fame in People magazine in August of 1982. And during the course of the time I was there, I was talking to the media, I was doing a lot of public information, but I also, because I had to talk to everyone, I needed to know what was going on. So I had the opportunity to work with all of the different monitoring groups. And also, in the early 1980s, any geologist from anywhere in the world who was anywhere in the US was coming to Mount St. Helens. It was an extremely exciting time for geology, so I really feel lucky to have had that opportunity. But I finally went back to grad school, and since that time I've worked all over the world. Volcanoes tend to be in nice places, so that's nice. But I have continued to come back to Mount St. Helens and work there every time I have a new idea or we have some sort of new technology and new way to look at the volcano. So that's a little about me. Now let's look at the volcano. The volcano had many different names in Native American, from the Native American tribes around the volcano. I won't butcher the names by trying to pronounce them, but apparently in translation, they all mean either fire mountain or smoking mountain. Well, that gives you some clues that it's a volcano. And this has become one of my pet peeves, because the European tradition, of course, is that you find a patron to fund you on an expedition, things haven't changed at all. We still need patrons, I think. And so when you're exploring, you name the mountain after your patron. And of course, this tradition, you then lose all connection to the place itself. So I still like to think of it as Fire Mountain or Smoking Mountain. And in fact, when the Europeans arrived in the Northwest, they found that there were lots of stories about this volcano. And I have a quote here from Paul Kane, who was in the area in 1847, where he says, "This mountain has never been visited by either whites or Indians. The latter assert that it is inhabited by a race of beings of a different species who are cannibals and whom they hold in great dread. Other stories call them skookums, and the skookums used to not only be cannibals, but they'd throw rocks at you." Okay, that's pretty indicative of what was happening. And so wisely, the native people stayed away from the volcano. When Paul Kane was there, he did observe and record in a painting the last eruption of the volcano, which was in the mid-1850s. The eruption that you see here created this lava flow, which was called the floating island flow. This is a picture before the eruption on May 18th of 1980. This is in the section of the volcano that is now strewn across the landscape. So the floating island flow no longer is evident. Okay, so why was this volcano so active? Why did it have these stories? Again, for those of you who are geologists, you know the answer right away. We are sitting here in the Pacific Northwest, and offshore to our west is an oceanic plate called the Juan de Fuca plate, and the North American plate is overriding that Juan de Fuca plate. So when the plate goes down, it starts to melt, and the melt comes up as magma and forms our volcanoes. The US Geological Survey developed this wonderful graphic that shows the main peaks in the Cascades and the eruptive activity from present back to 4,000 years ago. And it doesn't take a volcanologist to see that Mount St. Helens has been the most active Cascade volcano during this time period. In fact, in 1979, some USGS people published a bulletin on the past history of Mount St. Helens, and they predicted at that point that Mount St. Helens was the most likely Cascade volcano to erupt in the 20th century, and the next year it erupted. Some of that past activity created lava flows, like the picture I showed you, but there were past eruptions that were quite explosive, like the one in 1980, and the last explosive eruption before that was in about 1800, and there's this very interesting oral tradition from the area in northern Washington along the Columbia River, right near the Canadian border. And this story was collected in the early 1900s, and said, when my grandmother was a little girl, a heavy rain of white ashes fell. The people called it snow. The ashes fell several inches deep all along the Columbia and far on both sides. Everybody was so badly scared that the whole summer was spent in praying. The people even danced, something they never did except in winter. They didn't gather any food but what they had to have to live on. That winter, many people starved to death. So this is a very different type of activity and a different memory, or in this case, lack of memory prior to the eruption, because the people were living very far from the volcano, they couldn't see the volcano, and all they saw were ashes coming out of the sky. And we'll see both types of activity happened on May 18th in 1980. So let's take a look at the 80 to 86 activity and the transformation of the volcano from what many people considered to be the most beautiful Cascade Peak to what a lot of people now consider one of the least beautiful peaks. I don't consider it one of the least beautiful, but. So the first indication that anyone had that the volcano was about to wake up was a magnitude 4.2 earthquake that was located below the volcano on March 20th of 1980. Now, we've been hearing a lot about the the Haiti earthquake, which was a magnitude 7, and the Chile earthquake, which is magnitude 8.8. So a 4.2 is fairly small, but it's actually large for a volcano. There are some volcanoes that erupt and never have earthquakes larger than a 3. So this got people's attention. And in the week from March 20th up till March 27th, or I don't quite show you this here, but the number of earthquakes that were happening under the volcano ramped up significantly, so that by March 24th, you were getting about 30 earthquakes per hour. So it was pretty clear that something was going on under there. And then on March 27th, there were the first eruptions. They were small eruptions from the summit. You can see there's white steam there, and then there's black, mostly pulverized rock from the summit of the volcano. And these eruptions gradually excavated some holes or craters in the top of the volcano. And at the same time, there continued to be earthquakes. So this graph, or this diagram I show you, this is depth below the surface from 0 to about 16 kilometers, which is about 10 miles. And the activity in March, April, and May of 1980. And you can see in the 2 months before the May 18th eruption, there were just lots and lots of earthquakes, but they were very shallow. And then there were these explosions in the time period of the red arrows. But there was something else very strange that was going on. And it took people a while to actually get instruments out to measure it. But it's pretty apparent here that the volcano has this huge bulge on its side. And you can see it right here. And during the 2 months leading up to the eruption, the entire north side of the mountain moved to the north. And in fact, by the time they could monitor it, they could see it was changing moving fairly steadily. You can see these points on the north face between April 25th and May 18th moved north by about 4 meters. Now this is a mountain, and in fact, overall, it moved by about 50 meters. So there was definitely something going on there. And what we think was going on is that there was magma that was being intruded up into the volcano. It was shoving the north side of the volcano to the north. And at some point, that north side just collapsed under its own weight. In fact, there's still some debate about this. There was a magnitude 5.1 earthquake at 8:32 a.m. on May 18th that triggered this eruption. Some people say the earthquake triggered the landslide, but other people say the landslide was actually the earthquake. I mean, they were simultaneous. So there was a landslide that slid out to the north, and then that uncapped the bottle that was keeping the magma in, so you immediately started getting explosions both laterally toward the north and vertically. And because there were so many people around the area, it had been cleared out immediately to the north. People had been evacuated, but in the areas around it, there were many people camping. And in fact, a lot of them were geology and geophysics graduate students who were there with their cameras hoping to get something, get some pictures. And so there are some amazing photographic sequences. You may well have seen this one. I'll just show you a few of these. You can see very quickly the entire volcano disappears in this cloud of ash. And when people later got out in the field and could look at the deposits, it's interesting because you can see very close to the volcano, you have the landslide deposit, that's the pieces, the north flank of the mountain going down, and then this blast deposit on top of it. But you get out a ways, and the blast was moving faster than the landslide. So you get out a ways, and then you have, instead of landslide with blast, you have blast with landslide on top of it. There are a number of amazing stories. In fact, for the 20th anniversary of the eruption, the U.S. Forest Service invited back a number of the eyewitnesses and the people who had taken these photographs. So I knew the photographs very well, and it was fascinating to hear some of the stories. And the person who took this one was a geophysics graduate student. He was camped at an area to the northeast of the volcano. It was 8:30 on a nice Sunday morning. He had a little truck with a camper shell. He was lying in the back of his truck, sipping coffee, looking out at the volcano, and he had his camera there. And so he said that the eruption started, he's all excited. He gets to see it. He grabs his camera, starts snapping pictures, and he said there were 3 ridges between him and the mountain. And first one ridge disappeared, and then the second ridge disappeared. And by that time, he's out of the back of his truck, jumps in, and takes off and starts driving. But being a good scientist, he said he drove like mad for about 10 minutes. And then he's thinking and saying, if that cloud were continuing to move toward me at the rate it had been, it would have got me by now. So he pulls over to the side of the road, gets out of the truck to see what's going on, and it turns out the blast that had been moving north had encompassed enough air and heated up enough air that it became buoyant and it rose up above. And so there was this towering cloud up above him, and that's what this picture is. I don't think I would have had the presence of mind to think through that and stop and take another picture. Another of my favorite stories, the geologists went looking over the whole area and trying to collect people's photographs, and this particular mosaic was taken from the northwest. The volcano's here. This is that whole blast cloud that then picked up and started going vertically. And apparently this guy was someone who was visiting his brother, walked out on his brother's deck, saw this site, had never used a camera before in his life, picked up a camera that was lying around and shot this perfect mosaic. And in fact, it turned out to be very important because somewhere lost up in the specs, but you could identify a United Airlines flight that was flying between Portland and Seattle, and so they could actually time exactly when this mosaic was taken. So that was the first several minutes of the eruption, but then it was sort of interesting. Here is the seismic record, so this is a big earthquake, that's the landslide taking off, and you have the initial blast, but then it's a little strange. You have about 3.5 hours here where there was ash coming out, but the volcano was relatively quiet. And then around noon on May 18th, the activity really picked up, the seismicity really picked up, and the eruption really got going. So one question that I had always had is, what's this 3.5-hour gap about? If you shake up a soda bottle and take the top off, it goes right away. And so we'll come back to this. Just hold that thought. So right near the volcano, there were several things that happened during that several-hour time period on May 18th. There was the landslide, which we now call a debris avalanche deposit. It's very unique looking. It's got all these hummocks in it. And anyone who has driven up I-5 through Northern California, there's a huge debris avalanche deposit from Shasta volcano that went to the northwest, and you actually drive through it. And there are several of these debris avalanche deposits all around the world, and people never knew what they were until seeing Mount St. Helens. In fact, there's one in New Zealand that I knew about, and people just called them Lahar Mounds. But all of a sudden, the light bulb went on for volcanologists everywhere, and they said, oh, these weird structures are major collapse events of these volcanoes. The lateral blast knocked down, 150-foot high mature Doug fir forest, completely stripped the trees. Then you had a vertical eruption column that got going, and then that started to produce pyroclastic flows, which are these density currents of hot pumice and ash. This was actually taken in August of 1980. On May 18th, visibility wasn't sufficient to see those. And then there were also mud flows that were generated because these hot ash flows were going down into the rivers, and also the volcano had been covered with snow at the top, so you start melting the snow. And so if you look at the deposits, this is a map view. Here's the crater. This whole area is the blast deposit where the trees were blown down. This is a 5-mile scale bar, so it's about 225 square miles that were impacted by that. You then had this stripy deposit is that hummocky debris avalanche that went down the North Fork of the Toutle River. The brown are mud flows, and they went down all sides of the volcano, but the largest ones were when the debris avalanche dewatered, because if you take that whole north face of the volcano, it had a lot of water in it, and it generated mud flows that went down the Toutle River, into the Cowlitz River, into the Columbia River, and actually blocked shipping channels there. But there was something else going on, because you had this big eruption column, and of course here in the Northwest the winds mostly blow from the west to the east, so the ash was going off to the east, and tracking with the rate of the ash cloud by Yakima, by about 10 o'clock in the morning, the ash cloud had come over it, all the streetlights went on, it was so dark, you had ash raining out of the sky, and it continued across the state of Washington, over northern Idaho, hit Missoula, Montana about 2 in the afternoon, and even in Missoula they got several inches of ash. So imagine, everyone who was close to the volcano knew that this volcano was acting up and something was going on, but people in eastern Washington didn't at all expect to be dealing with ash. And ash isn't like snow. It doesn't melt. You actually have to physically do something with it. So I have just a couple of quotes or responses from people who saw this. I don't know if any of you are Ursula Gwynn fans. Earthsea Trilogy. She's a writer. She lives in Portland, apparently from her study. She could watch the volcano, and she wrote a wonderful essay over the several months of the summer of 1980 called A Very Warm Mountain. And I just have a few quotes from this. She said, "Everybody takes it personally. Some get mad, some take it ethically, but everybody takes it personally. We try to reduce it to human scale to make a molehill out of a mountain." And this is interesting because her whole essay, she's watching the news reports, she's listening to her neighbors, and she said that everyone sort of took it as almost a personal affront that this volcano had dared to destroy herself and blow ash everywhere. Another person who was very familiar with the mountain was Gary Snyder, who's a poet. He apparently grew up hiking around Mount St. Helens, and he was so distraught and so upset by the eruption that he said it was about 20 years before he even went back to the area. But he did, and he wrote published a book of poetry in 2004 called Danger on Peaks, and there's a poem in that about the 1980 eruption called Letting Go, and I just have a little segment from this that speaks to the distal ash. Roiling earth gut trash cloud tephra 12 miles high, ash falls like snow on wheat fields and orchards to the east, 500 Hiroshima bombs in Yakima, darkness at noon. So this is the impact or the effects that were recorded in that oral tradition from the north of the Columbia. Okay, so that was pretty spectacular. Was that it? Well, no. So the next question is what happened after this, and we'll look a little bit at why. So through the summer of 1980, there were a series of eruptions. They were explosive eruptions, and a couple of them took place during the day with good visibility. So I'm going to show you just another quick sequence from the August eruption. And keep an eye here, and what you're seeing are these, what we call pyroclastic flows, or these hot plumes or density currents of pumice coming down. You can see how quickly the ash what it's doing is it's incorporating air in front of it, it's heating it up, and it's turning into this roiling cloud. But when you get out and see the deposit it just leaves these sort of rubble piles of pumice, and then the ash goes elsewhere. So during that summer of 1980, gradually what you're seeing is that the rate of eruption was decreasing, and the eruptions were going from sustained activity that went on for tens of minutes, to very short pulses and then a pause and a pulse and a pause as the magma supply dropped. And eventually, in October of 1980, it ended with the eruption of this funny little lava dome that we called Muffy, because it looked like a muffin. And that Muffy is now at the core of the current lava dome. So that was the end of the explosive activity. And then throughout the rest of 1980 and intermittently through 1986, there were a series of eruptions that added lobes to the lava dome. So you'd have one lobe that come out, and then the next one on top of that, the next one on top of that. And you've got a dome that was this, like a stack of pancakes with all these pieces together. So that's what happened from 1980 to 1986. I wanted to tell you a little bit about what we learned about how the volcano was working, and in particular, how we could use it during that time to actually make predictions of what was going to happen. Now, during each of those dome eruptions, what happened is you have magma coming up from below, and so as it comes up, it breaks the rock around it, which causes earthquakes. And then it actually would push on the dome above, so it would push it up and out, so you could measure that deformation. And then that formed cracks that allowed gases to get out. So there were three different main things going on, all of which could be monitored and used to tell what was happening. Earthquakes are still the best way to figure out what's going on under the ground. And I showed you this graph before. Remember, these are all the little shallow earthquakes leading up to the 1980 eruption. When you have the big eruption, you see all of a sudden you get earthquakes down about 10 miles below the surface, so you have a very protracted system. And then before each of the little dome eruptions you'd see, or leading up to them, you'd see another little burst of earthquakes. And the earthquakes also told us there was only one other explosive eruption. That was a small explosion in March of 1982. And before that happened, for actually a few weeks before, we started seeing these very deep earthquakes. And so the seismologist said something a little strange is going on. In fact, for that, there were some Indonesian visitors. We were all at a potluck dinner at someone's house, and all of a sudden there's a phone. We're just about to have dessert. He picks up the phone call, and all we heard him say was, "What? 40,000 feet?" And immediately everyone's out the door. Another eruption. And that particular eruption, because it occurred when the crater was covered with snow, generated mud flows that went out of the crater here. So there was also deformation, and there was all sorts of deformation, but what I show you here were particularly interesting. This is a little fault or offset, and if you think of taking a rug and pushing it up against a wall, it's going to fold. And so because you had magma coming up in the center of the crater and it's pushing outward, but you have a crater wall that's confining it, you're getting all these folds or buckles. And if one piece is buckling over the other one, if you make a measurement from up here to down here, as it rides toward it, that line distance is going to shorten. And so you could measure that. And we did it just with pounding rebar into the ground. Rebar is a volcanologist's best friend, so rebar and tape measures, it was very low tech. But we could see, monitoring individual faults, that they'd be going along, nothing much would happen, and then all of a sudden the line would start to shorten. And in this case, at this point in time, a prediction for an eruption was issued. This was the eruption window that was given. This was when the eruption actually occurred. And in fact, every single one of the dome building eruptions was predicted in this way. There were also people out there measuring the gases, either using instruments looking into the crater or actually going out and collecting gases in the fumaroles. And taken together, measurements of the gas, usually sulfur dioxide, looking at deformation, and tilt, looking at seismicity, and you can see that everything was showing the same sort of pattern. So by using all these methods together, we could actually make very accurate predictions. Okay, so we've seen what was happened. We've seen how we could actually use it to warn people before individual eruptions. Now I'm going to back off a little bit and give you a little bit of Volcanology 101 here. And the sorts of questions that we want to answer is, where was the magma being stored before the eruptions? Why did the eruption style change from explosive to dome building? And also, why did the eruption end in 1986? So first, this is a tutorial on my favorite topic, bubbles and crystals. And you all know, assume that volcanic eruptions in the simplest sense, eruptions occur because there's gas, usually water and carbon dioxide, that's dissolved in the magma. And then as it comes to the surface, it is like taking the soda bottle off, and it comes out as bubbles that drives eruptions. And so this works, or this occurs, because if we're at a higher pressure, so if we're down in the earth somewhere at a high pressure, then we can dissolve a lot more water into a magma than we can at low pressure. And your soda is the same way. The reason that soda bottles, well, they're bottled under pressure so that you have CO2 dissolved in the soda, and then when you take the cap off and reduce it to atmospheric pressure, it bubbles, and that's the desired effect. So in a magma, if it comes up quickly, then the bubbles are going to expand, they're going to form and come out of solution, but they can't escape. So as they expand, they bring the magma with them, and you have an explosive eruption. If the magma's coming up slowly, then the bubbles can work their way out, and you get a lava flow. So again, using the soda bottle analogy, now if you were in my class and we could go outside, I would have brought, how many people have played with the Mentos and soda eruptions? Are there some kids in the audience here? So we actually do those experiments in class, but you'll have to imagine it. So we'll just take a soda bottle, and what happens, you release the pressure, you form some bubbles, they're going to expand, so that is going to bring the magma up, which releases the pressure more, which brings more gas out, and the whole thing accelerates up, and if that happens fast enough, you get explosive eruptions. So we know that happens, so then the next question is, well, how much water and CO2 was in the Mount St. Helens magma? Well, this is something that we couldn't measure back in 1980, but we have new techniques now that were developed maybe 20 years ago. And what we do is, this is an electron microscope picture of a crystal. So the Mount St. Helens magma had crystals in them that they were sort of millimeters in size. And as the crystals grow, they have imperfections, and so they'll grow around and trap some melt that they're growing from. And we can go into that melt and actually measure how much water and carbon dioxide is dissolved in the melt. And then, because we know how much you can put in at what pressure, we can then use that to say what pressure the crystal was formed at. Everyone got that concept? So this is just a plot. This again is showing depth below sea level in kilometers, so this is almost 10 miles. The gray are all the earthquakes that I showed you, and the bright pink and purple are our data from the melt inclusions. And you can see that the melt inclusions data is telling us that the earthquakes were actually recording where the magma was coming from. You can see a nice correspondence on 1980, but there's not as good a correspondence when we were having these lava dome eruptions. And we think that's because the gases were getting out and the little melt in the crystals was re-equilibrating because everything was having time. It was just sitting shallowly, and that's why it wasn't exploding. And there's one other thing I have to tell you, is that if you take water out, it actually causes crystals to grow. Now this might sound a little bit odd, but I bet a lot of you in the room have made candy of some sort, like fudge or lollipops. And anyone who's made fudge or made candy knows that you have to be very careful to monitor the temperature. So you make fudge, you put everything together, and you've got water and sugar and chocolate, and you heat it up. And as you heat it up, you're boiling off the water, which is concentrating the sugar. And in fact, the temperature is telling you how much sugar you have in solution, and that's going to control how it crystallizes. So it's a little bit different, but it's the same idea. If you take the water off, you increase everything else, and you form crystals. So what we saw was, again, these are electron microscope images. This is an image where the black are bubbles. The light gray is now glass, but that was melt. It was a liquid that quenched to glass. This was from May 18th, so all you have are bubbles and melt. But as we got in the summer of 1980, we started to see bubbles and melt, and then all these little gray things are little tiny crystals. That's 10 microns. So that is, a micron is 1,000th of a millimeter. So they're very, very tiny, but there are a lot of them, and those are growing because you're taking the water off and there's enough time for crystals to grow. And by the dome eruptions, you can see the crystals are quite a bit larger. So we have several things going on. The water's coming off, the crystals are growing, and all of that is affecting how the magma comes out of the ground. Okay, so now you've passed Volcanology 101, and we can actually go back to some of the questions we had at the beginning. So what was happening in March and April of 1980 with that bulge? Well, again, we think that magma was coming right up into the volcano, but it was coming up sufficiently slowly that it was actually forming all those little crystals, and it was getting stuck. And in fact, those crystals made it solid enough, I think, that that's why this magma was actually able to push the whole flank of the volcano to the north. So samples of that material that we collect from the blast, again, here's 10 microns. You can see there are very few bubbles, and you've got all these little crystals, and it was effectively acting as, concrete or even stiffer than that. And so this stuff was getting stuck in the volcano, and it was just pushing outwards. Whereas once the eruption got going on May 18th, and we really had a good connection from very deep to the surface, then we got the stuff that has bubbles and melt and no crystals. And so that's coming up rapidly from deep. So that says, we think prior to May 18th, there was stuff up here and there was stuff down here, and you were sort of feeding bits in, but there wasn't much of a connection between the two. And then between 8:32 and noon, what you were doing was opening up and building this through-going connection. And that's what took 3.5 hours before the eruption really got going. And that explains our gap. So we had to actually construct a conduit. And then I think over the summer of 1980, you started gradually then shutting that conduit down again. And first we developed these sort of interconnected storage regions, which we see because we have material in those summer eruptions coming up with different types of crystals. And this is an image that was developed by a process called seismic tomography, which is sort of like a CAT scan of the volcano. So they use earthquakes and figure out where there are earthquakes, they figure it's solid rock. Where there aren't earthquakes, they figure it's probably magma. And the tomography picture also showed all these little connected systems. And then finally, as time went on, this upper region, I think, was cooling and gradually shutting down to the point that you could no longer get magma out by 1986. I'm just going to skip that. So I call this my beyond the soda straw, because anyone who of you in here has taken a geology class and has seen a little schematic of a volcano, it always looks like there's a soda straw down to a bulb at the bottom. You know, that's how volcanoes work. So now I'm getting you to think beyond the soda straw. You have to build conduits, and then you have to keep them open. Okay, so that was the long part of the talk. Now we're just going to look quite quickly at what has happened since then. This is depth. These are all earthquakes. This is now 1980 to 1998. The shaded part here is when you were actually seeing eruptions come out. But did the activity, so after this time period, there was no evidence of activity at the surface, but had the volcano gone back to sleep? No. Look at what is going on. You have more earthquakes down here than you did when magma was getting out. And that's probably because you've got enough of a solid lid at the top. The magma can't quite get out, but it's still trying to get up. So you had all of these earthquake swarms that were indicating that you were still feeding magma into the system. And in fact, if we extend the record, now it goes from 1980 all the way out to 2006. You can see that you've got these seismic swarms. You also have this line of earthquakes that's sort of gradually going down, and we think that's a sort of solidification or some sort of thermal boundary that's gradually growing. It's a seismic, something is keeping the lid on the magma until 2004. And all of a sudden, we light up here, we start to see magma coming out the top, and we lose all those deep earthquakes again. So, by this time, we're now in September of 2004, and I was on my first real sabbatical ever. I had gone to Italy in mid-August, was planning to spend my sabbatical in Italy, and by the end of September, very quickly, the seismic records went from perfectly flat to looking like this, which was basically continuous seismic activity. By now, of course, everything's online, so I can log in and watch them, and I was getting more and more nervous. And I finally started talking to my travel agent and seeing if I could use my mileage plus miles to get back here, and I went to my Italian colleague and I said, I'm sorry, I'm going back to Mount St. Helens, particularly when that happened. And he said, okay, well, if you're going, I'm coming too. So I came back from Italy, and I was all nervous. I was talking to another Italian friend, and I said, you know, the volcano's going to start erupting and without me. And he said, Kathy, your volcano will wait for you. My volcano always waits for me. So I got up to Mount St. Helens on October 10th, and on October 11th, we saw this first little spine of new material coming out. So it did wait. And I'm going to show you this time-lapse movie. I'll show it to you twice because it takes a while to key in. The date is up in the upper right. And you can see that this is a very odd eruption in that it's just continuous, slow extrusion of this basically crystalline plug coming out of the ground. You can see it comes up, and then it sort of falls apart and moves over to the other side. So, you want to watch it again? Okay, these early forms, they were calling them whalebacks. I sort of thought of them as sand snakes. Anyone who's read Dune? And we were having debates, and everyone was placing bets. You know, was it ever going to get up above the crater wall? And it would get really close, and then it would collapse and fall back again. Okay, I'm going to show you a different one. Now this is, you're seeing a sequence again. I'll show it to you twice because it takes a while. These are digital elevation models looking straight down. So here's the old dome, 8086 dome. There's that whaleback. And then you can see another one comes out here. And then it falls apart. Another one comes out here. So we'll watch that. You can see it come out. It actually went till it was impeded by the crater wall, and then it started getting pushed up. It falls apart. Another one comes out and falls apart, moves over there. Now this time, don't watch the dome, but this was all a glacier. So keep your eye out here and on what's going on out here. And you'll see as the dome comes out, it's pushing the glacier aside and actually forces the glacier to move north out of the crater. Okay, so what's going on there? Well, you've had Bubbles and Crystals 101. You can say, it's now not coming out as a liquid at all. It's coming out as a completely crystalline, solid plug. And this is just another picture of it. So we think that the magma was coming up, but it was coming up slowly enough that it was degassing. The stuff is completely solid, and it's crystallizing. So by the time it gets to the surface, it's coming out as a solid. In fact, you can see all these striations on the side. It's actually forming like a fault gouge as it comes out. It's having to break. But it came out, it was coming out slowly, but very steadily, so that by the end of 2005, so in just a year and 3 months, it had already accumulated or erupted as much volume as the entire 8086 dome. And so it ultimately produced more volume than the 8086 dome. Why was this so different? Well, we don't really know. We're playing around. We had a student at Oregon do some modeling, and we think from petrologic evidence that the magma had cooled off a little bit in that 20-year time period. It was just a little bit cooler, and it seems to have allowed it to crystallize completely on the way out instead of not. But we're still, this is, again, it's a scanning electron microscope picture. It looks really messy, but the point here is it's completely crystalline. It's a solid block coming out of the ground, which does make you wonder why it's coming out of the ground at all. And why did it start up? We have no idea. And it's actually humbling to work on volcanoes because it makes you realize how much you don't know. So we really don't know why it reactivated when it did. We don't really know what it will do next, but you could see that you continued to have earthquake activity in that 86-2004 time period. So we expect that, and we're monitoring, or the USGS is monitoring, that if you're continuing to put magma in, we'll see that, and then we could have another reactivation. So with that, I will bring it to a close, take some questions, thank the University of Oregon, the National Science Foundation, who funded this, plus a whole lot of colleagues who have helped out, and grad students, and also thanks to my friend Bill Chadwick, who's at the Marine Center in Newport, and worked with me at Mount St. Helens in the old days, and he actually got around to scanning a lot of his old slides, which is why I have these in digital format. So thank you very much.
Different, but we've got a microphone over there that should be on, and for somebody over here, and again, this is just for the web feed so that folks can hear things. If you have any questions, if you can work your way over there while somebody is, again, if you didn't sign the sheets when you leave, if you could do that. There are also some posters for the April talk. If you have places to put them, feel free to go ahead and do that.
How did the gases change over time?
How do the gases change? That's actually a really interesting question. Typically, the gas that we monitor for volcanic eruptions is sulfur dioxide, and that's for two reasons. Number one, there's no background sulfur dioxide, so it's easy to measure. It's obviously difficult to measure water coming out because there's so much water in the air. And also, there are very cheap and efficient tools to measure sulfur dioxide because they were developed for air pollution monitoring. So prior to the May 18th eruption, there was actually very little sulfur dioxide that was coming out, and this was a puzzle to people. The thought is that it's very soluble in water, so it was probably getting trapped in the groundwater system in the volcano. Then during the summer of 1980, you were having a lot of SO2 come out, as well as a lot of carbon dioxide, and presumably water, but you can't measure it. And that died off over time. 2004 eruption there was very low gas. So there's about the right amount of gas for the amount of magma that came out, but there was not a lot of gas being stored there. So Mount St. Helens in general is a very sort of low gas volcano relative to a lot of other ones. And now it's pretty much background, but there's probably a lot of diffuse degassing. You can see some elevated both carbon, CO2, and also some other things like helium in some of the spring systems around there. So it still seems to be degassing, but there's not a lot of weird gas.
I didn't quite understand the striations on the crystalline plug. Could you revisit that?
Sure. That's something, it's called fault gouge, and when you have an earthquake fault, when two solid pieces of things slide against each other, one side will scrape the other. And so this material on the spine of St. Helens, it was both scraped as it came out of the ground, but also there was up to about 2 meters, so 6 feet, of what we call fault gouge, which is just plain ground up rock. And it looks very much like just a tectonic fault that causes earthquakes. So that was unexpected, and it was actually fairly unusual.
Thank you.
All right, I got a question. If the Juan de Fuca plate slips, it's been 300 years since it's significantly slipped. If it slips, is St. Helens going to erupt again?
Probably not. And that's an interesting question. Is there a relationship between subduction zone earthquakes and volcanoes? As far as we can tell, there haven't been in other parts of the world. So like there are several volcanoes down in Chile, several that are quite active. And as far as I know, they didn't show any unusual activity at the time of the Chile earthquake. And the same in Indonesia, that there are a lot of volcanoes there. So I think the subduction zone where the earthquakes happen are sufficiently far in space from the volcanoes that they don't seem to respond. Now, what's of more concern is if you have a big earthquake, that a lot of our volcanoes have fumarole systems and pretty, beat up rock, and they are prone to landslides and mud flows. And I can imagine that you could generate those, particularly if you have a subduction zone earthquake in the middle of a nice wet winter when the ground's pretty saturated.
Any additional questions?
Mineralogically, how did you classify the crystals you're looking at?
The bulk of the crystals are feldspar, so plagioclase feldspar, which is what you see in just about any volcanic rock that you pick up that has little white crystals is plagioclase. But there's also pyroxene and hornblende are the main phases.
Do you believe that in your lifetime you will have an opportunity to see another Krakatoa?
Well, we did sort of. Wasn't quite as big, but there was a pretty major eruption in the Philippines in 1991 of Pinatubo volcano that you may or may not be aware of. It wasn't quite as big as Krakatoa, but it was pretty good size. And on average, there's sort of one Krakatoa per 100 years. And so in the 20th century, there was a fairly big eruption in 1912 in Alaska, and then there was Pinatubo in 1991. So I guess it depends on how long I live. But my mom's almost 96, so I figure I got a long time, so maybe I will see another one.
Did the fallout of ash affect the weather pattern through years?
Oh, that's an interesting question. It certainly did right at the time. In fact, volcanoes are notorious for generating their own weather, and volcanoes will typically have a lot of lightning because the ash actually creates lightning. And then this eruption in the Philippines that I was telling you about was, it was a big eruption, and there was a typhoon nearby, and it looks like it changed the local pressure enough that it sucked the typhoon in, so it came right over the volcano, which then, of course, meant you weren't just dealing with raining ash, but you're dealing with raining mud, which is a lot heavier and tends to collapse roofs. Mount St. Helens, in terms of long-term climate changes, it's not the ash so much as this sulfur dioxide. And Mount St. Helens was a low sulfur volcano, but Pinatubo changed, it lowered the global temperatures for a couple of years afterwards. Not by a lot, but by half a degree. So what we really need to combat global warming is just a whole lot more volcanic eruptions.
So we'll take one more question, and then I'm sure Kathy would be glad to stand around in the lobby and answer some additional questions.
What type of mountain building activity accounts for the bulk of the mountain itself, as well as the other ones in the Pacific Northwest? How are they built, actually?
Okay, well, Mount St. Helens is a little bit different than some, and this is the perfect picture to illustrate this. See all this white material here and here? These were big, huge domes, like the current domes. So much of Mount St. Helens was built just by these big domes. However, about 2,500 years ago, there seemed to be a new batch of material that got into the system. And in fact, it generated almost Hawaiian-type lava flows off the south side. If any of you have been up there in the area around Ape Cave, then there are these beautiful lava tubes, and there are actually tree molds that you can crawl through if you're smaller than I am. And after that event of this sort of almost Hawaiian basaltic magma, then you got a lot of more fluid lava flows. And so you can see sort of in the crater wall here, there are very thin flows. So this particular one has big domes in the middle, and then it was sheeted over with these thin flows. And that's fairly typical. It's what we call a stratovolcano.
Okay, so I lied. One more question from this young lady, but before she asks it, again, thank you all for coming out tonight, and thanks to our sponsors, the College Foundation, also Oregon Resource Corporation, and NAGT. Ready?
Did the ash blow southward with the wind? Because there was rumors that it did.
On May 18th itself, it mostly went east. However, in those eruptions during the summer of 1980, I mean, Mount St. Helens was sort of an equal opportunity volcano. So on May 25th, the ash actually went west. And on June 12th, it went south. And then by July, it was going east again. So actually, everywhere around the volcano got ash at some point in the summer of 1980. They just got it at different times.
So thanks to Kathy for coming down and talking to us this evening. Thanks to all of you for coming out. Thank you.